continue with the module 4, which was basically having two parts. One part was feedback in amplifiers, the other part is coupling methods, frequency response of amplifiers and multi-stage amplifiers. Now, the one thing which we encounter, which is in general is very important for any amplifier, is its gain versus frequency response. Now, this will depend actually what type of coupling we have used. Coupling is required in every instrument. What is coupling? For example, we have a amplifier. At the input side of the amplifier, we have to connect the source. It may be oscillator, it may be a mic, or it may be some other electronic circuit that will send signals to be amplified in this amplifier. Now, how we connect it? You may say that connection may be through just a conducting wire. Well, that is one way. It has its own limitations and some better good points also. And similarly, at the output of the amplifier, for example, if we continue to talk about voltage amplification, then the amplified output has to be connected somewhere where it is going to be used. It can be a load can be a speaker, it can be a motor, and so on. So, how we connect that? So, there are various ways of connecting it. One of the very widely used method in particularly in discrete circuit, this was the most commonly used method of coupling. Even today it is widely used, and so that is RC coupled amplifiers. RC coupled amplifier. R stands for resistance and C stands for capacitance. But anyway, resistance is present already in the circuit and there is no external resistance required, but well, a capacitor is used for coupling. How? Let us see. A C amplifier, RC coupled C amplifier I am drawing, and this is this. This is the complete amplifier, which is a RC coupled common emitter amplifier. This is the signal which I said might be coming from a microphone or a oscillator, and this is to be coupled to this amplifier. This is basic amplifier. Now, this is the coupling capacitor C. This is for the time being let us forget about this, but this is another coupling capacitor which couples the load to the amplifier. Now, for this amplifier or in general for any amplifier, the voltage gain versus frequency response, voltage gain versus frequency response. For any amplifier, this is a very important characteristic of the amplifier. In general, we will get a response of this kind. This is frequency and this is, for example, voltage gain. What does it say? We are taking that the signal frequency is varied. We start with a very low frequency and then keep on rising, and so increase of frequency goes over few orders of magnitude. And we assume here that the signal strength does not change with the frequency. This is true for all good oscillators. If you are changing the frequency, the signal strength will not change. There are different knobs. There is a knob for changing different strength, how much is strong signal you need. Once you fix that, you change the frequency by moving a dial or a knob, or in steps sometimes it changes. Then, but the strength of the signal will not change, only the frequency will change. So, we are starting from very low frequency and then we are going to very high frequency. What kind of curve we get is this. That means, below a certain frequency here in this region, there is a fall of gain. Similarly, there is a region in which there is almost frequency independent gain. Gain remains constant when we are changing, this is frequency axis, when we are changing the frequency, and then again the gain falls. Now, we will discuss at length the reasons for the fall of the gain with frequency, but soon few points which we are almost currently assuming will be clear very soon. Now, here this is the gain at midband, M stands for midband, flat band, and then gain falls, and when the gain is 70.7, which is actually root 2 by 2 is equal to 0.707, and you will see the significance of these figures. So, when the gain falls at the value of 70.7% or 0.707 of AM, then we draw a line which cuts the frequency at 2 points. One is this is F1 and this is F2, and the bandwidth amplifier bandwidth is F2 minus F1. This is the bandwidth. These F1 and F2 are the cutoff frequencies. In fact, in most of the applications, the amplifier is used in this middle band. So, this is mid band region, here. This is from here to here, this is mid band region, and below this is the lower cutoff region, this is the upper cutoff region. Now, it can be shown that these frequencies are actually half power points. F1 and F2 are half power. because it is voltage, and power is proportional to a square of voltage. Now, as I said, 0.707 is actually root 2 by 2. So, I could have written here, instead of 0.7 I could have written 0.2 by 2, let us say the output voltage, here it is AM anyway. Now, powers are proportional to the square of the voltages, therefore, power at cutoff here, this is lower cutoff, this is upper cutoff. So, power at cutoff, and whether it is lower cutoff or at higher cutoff, power is the same. So, power at cutoff divided by power at midband, this is equal to, at midband, if it is the voltage is corresponding voltage is V. So, it is V square, and here it is root 2 by 2 into V whole square, and this is half. Therefore, from here we obviously see that power at cutoff P cutoff, power at cutoff from here, from this equation, this ratio is half. So, power at cutoff is half of power at midband. That explains that these points F1 and F2 are half power points. So, when the power falls from midpoint to half of its value, then that when it cuts this curve, it gives the lower cutoff F1 and upper cutoff F2 frequencies. Now, power levels in electronics and in electrical engineering are most often are described as another unit, which is a log unit called decibel. It is written with a small d and capital B, decibels. How as I said, it is a log scale, and when we describe the fall in voltage, fall in power, or the gains in terms of decibels, then we can use logarithmic algebra that we will see, and that makes the life very convenient and easy, and things can be manipulated very simply. This is defined, dV is defined as 10 log base 10 and the ratio of 2 powers. Power P2, it may be in watts or milliwatts, in the same unit we have to take power P1. So, writing simply the 2 powers P2 by P1 is good enough, and P2 by P1 is a ratio. So, it will be a number, and this can, taking log of that number and multiply by 10 will give you dV. For example, let P2 is equal to 2 P1, meaning that the power, output power is double of input power. So, that this ratio P2 by P1, we substitute P2 here. So, simply we will get dV 10 log base 10 2 P1 by P1, and they are cancelled. So, we are left with 10 log 10 and 2, and this comes out to be, you look for the 10 base 10 log for 2 and multiply by 10, it is very close to 3 dB. So, instead of saying that output power is double of the input power, we can say that the power level rises by 3 dB, and if that means there is a 3 dB gain in the amplifier. If P2 is 100 times P1, 100 times, then this is, as I said, it is log scale. So, this will be in dB, saying this, that output power is 100 times of input power, we may say that this in dB it will be 10 log base 10 into 100, and this is 20 dB. So, the amplifier has a gain of 20 dB, and so when this number in this expression, when this ratio comes positive, and if P2 is higher than P1, then it will be it will be positive, and number as we are seeing 10 dB, 12 dB, 50 dB or 20 dB, we can talk in terms of dB any powers. Now, if P2 is less than P1, if P2 is less than P1, what does it mean? There is no gain. In fact, there is a power loss. In that case, it will come in dBs, it will come in negative. So, let P2 as an example, let P2 be equal to 1 by 10 of P1, then in dBs this will be 10 log base, and this will be simply P1 will cancel out. So, it will be 0.1, and if we look for the log, then this will be minus 1 dB. So, if the power at the output is 1/10 of the power at input, then we may say that it is minus 1 dB. Power levels at midband and power levels at cutoff frequencies, they can be similarly related. So, the power we can write in dB, this is 10 log 10 power at cutoff here, or here, cutoff divided by power at midband in the frequency independent region, and we have said that this is half. We just find out that power at cutoff is half of power at midband. Power here is half of power here. In dB, this means this is equal to 10 log 10 by half, which is 0.5, and this is approximately minus 3 dB. So, power points F1 and F2 are also called 3 dB points. 3 dB power is down from midband frequency, midband power. We can talk, so far we were talking in terms of powers, but as we know that power P is proportional to voltage square. So, we can talk in terms of voltages. how much is the fall in voltage or power gain, the voltage gain, voltage fall, this all we can discuss in terms of dVs. So, using this, that power is proportional to the square of the voltage, we can write in dV in terms of voltages, dV is equal to 10 log base 10 V2 by V1 square. If we take this square this side, this becomes 20 log base 10 V2 by V1. So, in terms of power and voltages, there is a difference. There it is 10 log, here it is 20 log in terms of voltages. Now, if V2 is 10 times of V1, in dVs we will say, 20 log base 10 10, and this comes out to be 20 dV. So, if at any point if the voltage rises 10 times of the previous value, then we say that it has gone up by 20 dV. And similarly, if V2 is half of V1 or which is 0.5 V1, then dB, in dB this is 20 log 10 into 0.5, and this comes out to be minus 6 dB. If the voltage at any point of the circuit falls half of its previous value, then in terms of dV we say that the voltage has fallen by 6 dB. Minus sign indicates the fall and plus sign indicates the rise or gain. And then we apply rules of logarithmic rules are applicable, as I said, that makes analyze the calculations much simpler. Let us take for example, we can use this fact that since V2 by V1, when this is equal to 2, it corresponds to 6 dB. Then if the voltage gain is 4, voltage gain is 4, then 4 is equal to 2, and the product in log scale becomes the addition. So, this is equal to 6 dB plus 6 dB. So, it is 12 dB, and we can extend it for voltage gain of 40, voltage gain of 40 in dVs we can write 40 is equal to 2 into 2 into 10, and we know this is 6 dB, this is 6 dB, this is 20 dB. So, this is 6 plus 6 plus 20, 32 dB. If we take false, then let the voltage falls to 1000, that is V2 by V1 is equal to 1 by 1000. Now, 1 by 1000 is equal to 1 by 10 into 1 by 10 into 1 by 10, and 1 by 10 we have seen earlier, this is equal to minus 20 dB plus minus 20 dB plus minus 20 dB. So, this is minus 60 dB. If the voltage at a point has fallen to 1,000th of its previous value, in terms of dV it is fall, and we say that voltage at that point has fallen by 60 dV. So, it is much convenient to talk in terms of dV, and engineers and scientists very widely use this dV scale. You must develop familiarity by calculating various numbers into decibels, and so dV is very widely used, and that is why we have taken here. We took an example of the RC coupled amplifier in the beginning. We continue the analysis that suppose we want to design a amplifier in which the lower cutoff frequency f1 is given, that keep it for example 100 hertz or 1 kilohertz like that, then how we can design it. It is so, this is the analysis of the RC coupled amplifier. So, coupling capacitors, let me tell you one fundamental thing about this, which I will anyway go do it now in details. This is the coupling capacitor, this is also the coupling capacitor. For the time being, let us just consider this coupling capacitor. This fall in gain, this F1 comes because of this capacitor, that in the mid frequency region the reactance of this capacitor is not much, and the voltage, the signal, because when the signal passes there is a mild drop here, and that drop of signal across the capacitor is insignificant in the mid band region. But as we decrease the frequency, then the reactance will gradually become more and more important. There will be larger and larger voltage, signal voltage drops, and whatever signal drops here is not available, that is not going inside at the input of the amplifier, that is the waste, not recoverable. This is not desired, but anyway this is the evil necessity where we want to couple. Now, the coupling capacitor is doing two jobs here. One is that it is coupling the signal to the amplifier, this is one, this is what we want, and another point, another part which it is playing, that any DC signal, a DC voltage from the source side, from the previous side of the circuit also is blocked completely. You will recall that through a capacitor DC cannot pass. So, this DC, if there are several stages, RC coupled stages, from DC point of view all stages can be individually analyzed and designed, and they will work perfectly all right, and RC coupling is used. So, this is the coupling capacitor, and it is doing two functions. We are concerned here with the only one function. The other function is it is blocking DC, and the primary objective here is coupling, that how effectively it couples. So, this is that. Now, we analyze the effect of this capacitor, and what is the expression for the cutoff frequencies, which if cutoff frequency is given, we can choose the components like capacitor at accordingly, and if capacitor suppose is given that this value of capacitor has to be used for coupling, then we know what will be the cutoff frequencies. So, coupling capacitors and low frequency response. for analysis purposes only one capacitance is sufficient. Actually, as I said, there is a capacitor at the output also, that we will take little later, and the circuit is this. This is the C amplifier, and this is the coupling capacitor. This is the source resistance which every source has, and for the sake of completeness we are considering it. So, this capacitance C is the coupling capacitor. It couples the signal to the amplifier, and here this is the voltage between this point with ground, this is V in. This is the actual signal. Out of Vs, V in is effectively going to the amplifier. Now, when we say that in this frequency region the gain is falling, actually the reactance of this capacitance is significant at those frequencies, and as we lower the frequencies, reactance which is 1 by j omega c. So, lower the frequency, higher the value of reactance of the capacitance, it increases, accordingly the drop increases, and so that explains why the gain falls. Very important statement. For this lower, in the lower cutoff frequency region, the coupling capacitor is responsible. How lower will be the F1, the lower cutoff frequency, that will depend on the value of coupling capacitor C. Now, this we can for analysis purposes we can Thévenize this circuit, and a prototype circuit can be drawn. Prototype circuit, where we will replace this by a Thévenized resistance. So, that is, we measure here the resistance R in, Thévenized resistance, and so the prototype circuit becomes this. This is the capacitor, Rs the source resistance, and R in is Thévenized input resistance of the amplifier. Thévenized input resistance or impedance. At low frequencies, impedance and resistances are same. So, they are used loosely, there is no distinction. So, Thévenized input resistance. Now, this is the prototype circuit for the analysis, and how much is the current I in the circuit? We can simply write the applied voltage Vs, and these three components, the source resistance, the coupling capacitor, and the Thévenized input resistance of the amplifier are in, they are in series. So, we can write for the current how much will be the current in the circuit. The current in the circuit is I equal to V s divided by the total resistance, because they are in series, R s plus R in minus j x c. X c is the reactance, X c is reactance of the capacitor, which is equal to 1 by omega c, and this is when it is j, then this j can be put up, taking both, you have done it many times, that put another j here and one j here, multiply by j, divide by j, that will become minus sign and one j will be left. So, it will be this, and the input voltage, to the amplifier what input voltage? This one, V in, this is the input voltage, and now we are seeing this is a function of signal frequency omega, here omega is coming. So, the input voltage of the amplifier V in is V in equals to R in, whatever is voltage appearing here, this is V in, with here between this and ground, between this and ground, this is V in. So, the current is flowing and that current is equal to this. What is the voltage developed here? That will be this resistance, and R in by R s plus R in minus j x c into V s. V s will be equal to V in if R s is negligibly small and reactance is also 0. I repeat, look here at this expression here, V in is equal to V s, almost equal to V s if R s negligibly small, tending to 0, and reactance is also tending to 0, then this is true, and the whole signal is falling on the, is going to the amplifier. Let us continue the analysis. This happens actually at the mid band, but we will say it differently. The magnitude of V in, as a function of signal frequency omega is this. The magnitude of V in, we take the real part of that, and that is R in R s plus R in square plus x c square into V s. This is the magnitude of the signal which is going from which is going into the amplifier. This is the magnitude, and the phase angle theta between V in and V s, and the same phase angle will appear between output voltages and input voltage, and this is theta, which is given by theta is tan inverse x c r s plus r in. In this unit, let us renumber the equations. Let this be equation 1, this is equation 2. Now, we discuss the midband and the lower cutoff region and come out with an useful expression which can be used to calculate the value of capacitor for a particular cutoff value. These two equations. Now, case 1, at midband we are considering at midband. In midband, the reactance of the capacitor is negligible in comparison to this. This reactance is negligible in comparison to this, that is R x c is very small as compared to R s plus R in. This is how the midband is defined actually. At midband, this reactance of the capacitor is much less with this reaction with this resistance R s plus R in, and in this situation the voltage drop across the capacitor is taken as 0. The voltage drop across the capacitor C may be dropped, then from this equation here this is dropped, then what we get V in simply equal to R in by R s plus R in and magnitude V s. This is there is nothing here, these components are not frequency dependent, and hence the gain at the midband, this is for midband. The gain at the midband is frequency independent. Here this is almost frequency independent, and here by the because the reactance is negligible, if we neglect, if this we take tending to 0, if x c tends to 0, then theta will be tending to 0. So, there is no phase angle between signal V s and V in. So, that is why we get at the midband frequency independent behavior of the amplifier. Let us consider another case, case 2. This is another extreme case. The one extreme case is this upper one, and the other extreme case is let omega be equal to 0. That means, we are talking of DC signals. The frequency of the input signal drops almost to 0. In this situation, when omega tends to 0, the angular frequency of the signal, then reactance tends to be infinity, and in this case this will completely block DC. So, V in, the signal which is going in the amplifier, will be 0 and the output signal will also be 0, and theta, the phase angle in this situation, if we substitute here theta this xc as infinity, then theta comes out to be 90 degrees. So, these are the two cases, extreme cases, one when theta is 90 and the other situation where theta was 0, and that 0 happens in the mid band, and this happens for DC just the extreme left point of the curve. From here let us examine this case. This is the third case, is most significant, case 3. Let us examine the situation, what happens when the reactance becomes equal to the series resistance of the amplifier, of the circuit, the prototype circuit, the RC network which we draw. This is the prototype RC network. So, if Xc is equal to the two resistances, then under this condition from equation 2, this is equation 2. If the two are equal, then you know this will be tan inverse 1 and theta will be 45 degrees. So, theta from equation 2, theta equal to tan inverse 1 or theta is 45. Substituting this, we get, if we substituting Xc is equal to Rs plus R in equation 1. Here in this equation, if we substitute this, we get V in is equal to root 2 into R in Rs plus R in into Vs, and this is mid frequency. This happens at mid frequency. So, V in is equal to root 2 of V in at mid frequency. At mid band, 0.707 of V in at mid band, or simply fall of 3 dB. So, that this defines the cutoff. This condition is used, Xc Rs plus R in, or it defines the cutoff frequency. Let us call, let the lower cutoff frequency be F1. Then let us substitute for this reactance 1 by omega c, and omega is 2 pi F1 into C, the value of that coupling capacitor. This is equal to Rs plus R in. From here the frequency F1 is 1 by 2 pi Rs plus R in into C. At midband, the angle theta was 0 degrees. At the other extreme, theta was 90 degrees. So, when we lower the frequency from midband, the point at which theta is 45 degrees, that is achieved when the reactance of the capacitance is equal to the other series resistances in the circuit, then we get this. This is the lower cutoff frequency. If we know the value of R in, which is the Thevenized input resistance of the amplifier, and this is the source resistance, then we can find out the cutoff frequency. We can write in journal actually this equal to 1 by 2 pi R effective, which may be R effective, maybe for example R s plus R in, or if R s is 0, then it will be simply 0 or very low in comparison to this, then it will be simply R in into C. This is the expression for the lower cutoff frequency, and this expression we can use if we know the value of this capacitance, then we can find out the cutoff frequency below which the circuit is not normally used. And if we know F1, if we are given F1, that calculate the value of capacitance if these effective value of resistance associated with that circuit is known, then we can find out the value of capacitor. So, this is the analysis of the effect influence of the capacitor on the low frequency performance of the amplifier. As I said, RC coupled amplifiers are very widely used. This analysis is very important, and we have completed the analysis. We know if we know this value, we can find out the cutoff frequency. Now, as we increase the frequency, the influence, this becomes almost, the capacitor becomes almost a short, and there is no effect of it. Then why the gain falls? We will see later that the reason for this is junction capacitances associated with the circuit. So, remember, low frequency cutoff comes from coupling capacitors, high frequency cutoff comes from junction capacitances. So, at this point I stop for the time being, and we will continue.